Alright, welcome to Light. Today we are going to be looking at what reaction of alkynes. We have a lot of reaction, but we are going to be looking at the most important first 10 that you're actually going to be needing for O level and A level too. So now I'm going to be telling you in this video how the reaction works, the mechanism, and also I'm going to be telling you the intermediate and the final product, and also the terms and conditions which the reagents here like a as looking at this, we can see these are the names of the reaction. Now, these are going to be our reagents, and these are going to be our final product. So I'm going to explain everything to you. So stay tuned, okay? Now, the first one we have here is combustion. Now, we all know that alkyne is born very sooty because what they have high carbon content compared to the alkenes, or rather alkenes. Okay? Now, if oxygen happen to like meet any hydrocarbon, it normally undergoes either incomplete or complete combustion. So now, but here this one present here is complete combustion. It's going to give us a product of what? CO2, which is what? Carbon dioxide and water. But if it's incomplete, it can actually undergo incomplete combustion, and it's going to give us what? It's going to give us CO if it's incomplete combustion. Maybe there is limited supply of oxygen. So now let's move over to the next one here. Now this one is interesting. Hydrogenation. Now this hydrogenation is a little bit complicated because it's kind of depends on the condition of the reaction that will determine the product. Now, first of all, the hydrogenation means what? Addition of hydrogen or molecule, which means two atoms of hydrogen are going to be added. So don't get confused. Don't go and think it's just hydrogen atom. Okay, hydrogen molecule is what is going to be added. That's the definition. So now let's look at the reagents and the conditions in which we are going to get our corresponding product. Now, if we use palladium, nickel, or platinum, anyone, I didn't write platinum here, but we can also use it. If we use palladium, nickel, and platinum, what is going to be our product? Now, see what we are going to get. Obviously, our product is going to be alkenes. Direct, like it's going to like reduce it direct to what? Alkenes. But now we have an unknown guy here. Probably you might have heard him. I don't know. Lindlar's catalyst. I don't know if you've heard him. But now let me present it to you. Lindlar's catalyst is technically a what? Poison catalyst. Why do we say so? It's because the component actually comprises of what? Poison. Now, first of all, it composes of what? It composes of what? Palladium and what? Borium sulfate. And that's not all. Then this is now where we say it's technically poison catalyst, because quinoline is actually the poison we are talking about, which poisons the catalyst. Now, if we use this poison catalyst, actually there are two ways of preparing this poison catalyst, calling that catalyst. We can use the one I just called now, or we can use this other method of palladium with calcium triazocarbonate, yes, and finally lead acetate also acting as a poison, the way our quinoline was acting as a poison. I actually explained the whole mechanism of how this Lindlar's catalyst is being, the whole structure. I drew everything in a more detailed video where I actually explain everything here one after the other. Here I'm trying to summarize, so I'm not really giving the whole gist. Okay, so if after you've watched this video you've gotten a glimpse of the reactions of alkynes, you can decide to go and watch that video if necessary. So now let's continue. Now, when we use this Lindlar's catalyst, what is going to happen? It's actually going to reduce the alkynes to what? It's a reaction of alkynes. It's going to reduce the alkynes to what? An alkene. And not just the normal alkenes. It's a what? A cis alkene. Now, how do you put it to your life? I like to remember this Lindlar's catalyst as cis-Lance catalyst. You get it? Like putting the cis instead of links. Okay, so put it in your head like that, you will never forget it. Now remember, this catalyst to give you alkene direct. If we use this one, it's not just going to give you any alkene, but it's going to give you what? Cis alkenes. Okay, all right. So now moving downwards, we have halogenation. Now this is interesting, very very easy. Don't get confused. Now the key point here is halogens. It's actually a what? Nucleophilic addition of what? Halogens. Example of halogens like bromine and chlorine. Now, if we first of all use one molecule of these guys to attack an alkyne, what are we going to get? Now we're going to get what? A dihalide. Now, if you don't know what dihalide means, you don't know what tetrahalide, I made another video, about 1 minute or so video, explaining, check it out, explaining what dihalide, tetrahalide, and the types of dihalide we have, like geminal dihalide and vicinal dihalide. Okay, so on that note, let's move forward. I said if we use 1 mole of these guys to attack what the alkyne. It's going to give us what? It's going to reduce the alkyne from triple bond to double bond, giving it what? A dihalide. It means two halogens will be present in that reduced alkyne to alkene. Two halogens will be present. Then aside from that, if we now use two molecules of the halogens to further react, or we can just say if there is excess of halogens, either bromine or chlorine, we are going to get a straight product of what? Tetrahalides. Now let's move forward. Okay, now hydrohalogenation. Now I like to break down my stuff. First of all, we have hydro. It means it has to do with what? Hydrogen. We are adding hydrogen. It's all this reaction is also a nucleophilic addition. We are adding hydrogen and what again? Halogens. Okay, get the keyword hydro that is stands for hydrogen. Halogens, we know that. Okay, so now how do we now add these two? Easily, we know what we call hydrogen what? Halides. And these are examples of hydrogen halides. Very obvious here. So now, if we happen to now react this guy or this guy with an alkyne, what is going to happen? We are going to get what? A vinyl what? Halide. Now, what do I mean by vinyl halide? We are going to now, it means vinyl halide means when a what? Halogen is attached to a carbon near the what? The double bond. A carbon near the double bond, you know it's going to reduce it to an alkene, obviously, from an alkyne to an alkene. After reacting these guys, the hydrogen halides, after reacting them with the alkyne, what is going to happen? It's going to reduce them to an alkene. Now, which alkene? That's the vinyl halide we're talking about. So now, defining the vinyl halide, we mean a halogen close to what? The carbon with the what? Double bond. Or what? Triple bond, it depends on the either alkene or alkyne. Okay, so now moving forward, what happens? How do we now get this other product? It's when there is excess of this guy. That is 2 moles. If we use 2 moles of this guy to react the alkyne, it will give us what? A geminal dihalide. What do we mean by geminal dihalide? It means when two halogens are that are connected to what? One carbon. I made a specific video differentiating these halides, like the halide, tetrahalide, and the types of halide like this. Now I said that earlier, okay, so you can go and check it out if you don't understand. Okay, so now finally, okay, we still have more, sorry. Okay, we now have a hydration. Now, from the word hydration, we can obviously tell that it has to do with addition of water. But now, how we be able to add this water? It's simple. It's actually an acid-base reaction. Now, on this note, we are going to need a mineral acid, and obviously we have our mineral acid here. And that's not all. For this reaction to actually work, we also need what? Mercury. We also need a mercury. So now, adding this water here to an alkyne under the condition or the presence of what? A mineral acid and mercury, what are we going to get? An enol. But obviously, we all know that enols are not stable. They are not stable. So they undergo tautomerism to do what? To turn to ketone. That ketone is actually our final product. This guy is not stable. Okay, it can't stay in this form. It's hard to undergo tautomerism, and to be able to stay comfortably in the position, it has to change to a ketone. Okay, all right. Now looking at number 6, hydroboration. This reaction obeys what? The anti-Marconi rule. As this number 4 here, hydrohalogenation obeys what? Marconi rule. This one is anti-Marconi, this is Marconi rule. Now, what is Marconi rule? This is what? The reaction between what? An alkene and what? And what? Hydrogen halide to give us what? An alkyl halide, also called haloalkanes. Do you understand? Now, the Marconi rule is what? In the presence of what? Sorry, in the absence of what? A peroxide. But here in the Marconi rule, there is a presence of peroxide for it to be called anti-Marconi. Okay, now from this peroxide here, we obviously know the definition is correct. Okay, so now which compound is this? This compound is what? BH3. It's called what? Borane. Now, when we want to hydroborate an alkyne, what do? We have conditions. As we said, it's following an anti-Marconi what? Reaction. Now, for us to get our desired product, You know we are aiming what to get an aldehyde. We need a terminal what alkyne for this reaction for us to be able to get our desired product. So now, using a terminal alkyne to react borane in the presence of what our peroxide here, hydrogen peroxide, and what mercury, we are going to get our aldehyde direct. Okay, so if you need further explanation of that, go and check the other video. Okay, now 7, ozonolysis. Okay, now this ozonolysis is very very simple. There is no too many talk about it. An alkyne react to what we call it this ozone, right? It reacts with ozone or react to what permanganate, potassium permanganate. If you react with this, it will give us what a carboxylate, but there is a condition for distance. Okay, now see what happens. It's actually an oxidation reaction. We oxidize what? We oxidize our alkyne to give us our carboxylic acid. But now, if it's a terminal alkyne, it's going to give us what? CO2, carbon dioxide. But now, if it's an internal alkyne, something is going to happen. It's going to give us what? 2 carboxylic acid. It will like split. You know now, is an alkyne. It has triple bond. It will split the carbon bearing the triple bond, and each will become a carboxylic acid. Now, on that note, let's look down. We have what? Acetylide formation. Alright, this one is very very easy. When we have what? An alkyne, we react. We need a very strong base for this thing to happen, and obviously we have the guy for it. We have the plug, either sodium or what? Sodium imide will work for this reaction. When we react the what alkyne with what? A very strong base, something will happen. It will what? Remove the acidic hydrogen present in what? The alkyne. This is to tell you that what? The alkyne must be what? A what? Terminal alkyne for this reaction to take place. Do you understand? It must be a terminal alkyne. So now when we react the base, it will now remove the displaceable hydrogen that making what? The alkyne very acidic, and now give us our acetylide ion. Now, this is actually what we are going to get. This compound here is called what? Sodium acetylide. That's what. Now, do you know that this number 8 is related to this? For us to perform alkylation, we must first get what? Our acetylide ion. So it's like a two-step reaction. So what I'm trying to explain is that in alkylation, this acetylide formation is also under it, but I separated it here so that you don't get confused. Okay, now after we've gotten our acetylide ion, now what is the aim of alkylation? Is to get a longer carbon chain, right? And we already have our acetylide ion. We just need to react this acetylide ion with what? An alkyl halide. When we react the alkyl halide with the acetylide ion, what will happen? We are going to get a longer chain alkyne with an extension of what? 1 carbon, depending on what the alkyl halide you are using. If it's an alkyl halide that has 2 carbon, we are going to extend the alkyne by what? 2 carbon. Hope you understand. Now, finally, looking at this is for this longer chain alkyne. Okay, so now finally, sodium or what? Ammonia reduction. Now, this reaction is a reduction reaction of what? An alkyne. How does this take place? It has to do with what? The addition of what? Hydrogen molecule. How do we add this hydrogen molecule? It's under the condition or the presence of what? Sodium plus what? Liquid ammonia. The two together does this work. So in the presence of these two, we will now what? Reduce an alkyne to an alkene. And which type of alkene? Obviously is a what? Trans alkene. Now, this method of getting the trans alkene, it kind of looks like this guy we explained before. The what? Lindland catalyst. The Lindland catalyst is going to give us what? An alkene, but a cis alkene. Here now we give us an alkene, but a trans alkene. So they're like opposites of themselves. Please note these two reactions. Okay, thank you for watching. If you know you need more explanation, more detailed structuring, because here I didn't expatiate on the structures. If you need those detailed structuring, please check out the other video. Alright, thank you for watching. Make sure you press the like, subscribe, don't forget, so that you can get more explanation and more teachings of chemistry.
Hello, Oga. would you keep your son here from morning to night?
I want problems always.
God have mercy upon us. Hello, Papa.
Open your mouth.
Hello, Papa. They kidnapped me. Oh. They kidnapped me.
Where your mama use chop? Where do you chop? Where you live for this kitchen? Now who got water?
Water? That man had the boss. Who water?
I said they kidnapped me like I'm in the custody of...
Me as I ask, who for kitchen?
Ouch.